Good afternoon, ladies and gentlemen. I think we're going to get started with this program. And this is the McEllhiney Lecturer Series. I am chair of the McEllhiney Lecturer Task Force, and we welcome you all here. We work very hard to come up with some outstanding speakers, and believe me, I've listened to them already. So when I exit the room shortly, I have another commitment. I have heard him, and you're in for a heck of a treat. Continuing on, the restrooms are in the two corridors, men on this side, women on the other side. There's a yellow sign-up sheets that'll be passed around for your certification. A number will be assigned at the end of the lecturer, so you know what the certification number for your state CEUs is. And at this present time, we want to make a little presentation, and I call past lecturer 2010 McEllhiney lecturer Mike Meemer to come forward, please.
Tom, I'm going to suggest that, does anybody know if Tom Christofferson is in the room? I haven't seen him, but I'm here to, on his behalf. Tom was the lecturer last year. Many of you probably heard it. And on his behalf, I'm going to accept his plaque and I know he thoroughly enjoyed his year of service and helping out the organization. So I was here to present this to him, but nobody's seen him. So thank you, Tom, and we'll see that you get this. Thank you.
Thank you, Mike. This program is available because of some great sponsorship for the last several years, and we want to thank Franklin Electric. So upon completion of this lecturer, and you go into the exhibit hall today and tomorrow, please stop by the Franklin booth and thank them for their support for this great program that we have here. And at this point, I'd like to introduce a representative of Franklin Electric, Mark Reeder, who currently serves as Franklin Electric's Director of Field Marketing, responsible for Franklin's North America Field Services efforts, and directs a team of 15 field engineers, as well as Franklin's technical hotline in Bluffton, Indiana. He's got a lot of other stuff here that he does. He's a very busy man, and he holds a degree in engineering and business. So at this point, Mark, would you come forward to make the introduction? Mark's been with Franklin Electric since 1995. Mark.
Thank you, Richard. Good afternoon. On behalf of Franklin Electric, it's my pleasure this afternoon to introduce the 2012 McEllhiney Lecturer, Marvin Glotfelty. Marvin is the co-founder of Clear Creek Associates. That's a groundwater consulting company. It's got offices in Tucson and Scottsdale, Arizona. Marvin's a licensed water well contractor, well driller in the state of Arizona. And since 1990, he's been the technical director for the Arizona Water Well Association. I'm really kind of in awe of Marvin's resume. He also has a Bachelor of Science and a Master of Science in Geology from Northern Arizona University. And he's been involved in the design, installation, rehabilitation, or abandonment of more than 600 water wells throughout his 20-year career. In 1995, he was recognized by the city of Phoenix, by the mayor there for environmental excellence for his rehabilitation of municipal wells in the city of Phoenix. The Marvin's lecture this afternoon, as we kick this series off, is a life cycle economic analysis of water wells. And when I first saw that, I thought, boy, that sounds pretty academic. And then I read on and got into it a little bit, and it's actually based on actual data on the total life cycle cost from more than 70 wells between 1993 and 2010. So it's not academic at all. It's very down to earth and sounds very rigorous. And I, for one, am very much looking forward to it. Marvin?
Thank you. Can you all hear me okay with this mic? Great. Well, as you said, this is the McEllhiney Lecture. It's a great privilege to have been selected for this. So I'll just get right into it. This lecture series, as you may have heard some of the other presentations, is in honor of the founding president of what was the National Water Well Association, now the National Groundwater Association. Back in 1948, William A. McEllhiney was a groundwater contractor and engineer, and so I guess I feel a kindred spirit to that, being both a licensed driller and a hydrogeologist. McEllhiney really meets a lot of the intent of the National Groundwater Association, which intends forums such as this to be a clearinghouse for dissemination of information and such. This really hits that dead on with the intent of being the McEllhiney presentation to being applied well technology. And you'll see that there's a lot of feet on the ground technology being presented here today. Starting in 2005, this program has been underwritten by Franklin Electric. We greatly appreciate the support that they have provided to this presentation as well. So I'm Marvin Glotfelty, your lecturer for 2012, and my topic, I would like to mention so that folks in our California and Virginia offices don't give me a hard time, that we also have offices in Leesburg and Claremont. So my topic for today is and for 2012 is life cycle economic analysis of water wells, considerations for design and construction. So we'll go through a lot of information in the next bit of time here. Prior to that, though, I wanted to extend appreciation to some folks that made this possible. Couldn't have done this without information being provided from City of Phoenix on their water operations information. You have to roll that into a economic analysis. Carollo Engineers provided information on water treatment for comparison between things that can be done in a well design versus wellhead treatment. A lot of suppliers here, Carmuse Industrial Sands, Johnson Screen Company, and Roscoe Moss Company provided information so we could have current 2011 information on the economic analysis, plus some historical information. And the Weber Group LC from Chandler, Arizona, a pump contractor, provided information on pump and motor costs, and also some of the operational costs, some cleaning costs, et cetera, that were embedded in this study. Further, most of the information that's presented in this I learned after college from well drillers. So thank all of you for that. Here's a lecture outline. We'll go through this straight through. First, to get a background, so we're all on the same page, I want to go through well design and installation overview. This will be the way things are done in my neighborhood. Might be different than a lot of places around the nation, but a lot of the results really will come back to the same. Then we'll talk about the impact of hydraulic gradients on wells. It can be a great economic impact, both in terms of the physical availability of water and water quality. We'll then talk a bit about how we could go to existing wells and try to do this old house approach, fix the old wells, which can be done in many cases. Then that kind of sets the background for the economic analysis, which comes in two parts. The first part looks back in time. So we do a time series analysis looking back 18 years, back to 1993, looking at 70 wells, at what the costs were, how they changed. Then we look forward in time, looking at different types of wells and how they might benefit us. So really, what is the most cost-effective way to put in a well? That's the question that we'll address. The reason we'll address that is I find with a lot of water purveyors, contractors, hydrogeologists, and others, that we have a lot of focus on the initial cost of a well. So the initial cost of the well, we can include, of course, the installation of the well. The capital cost of installation includes our driller, the construction materials, permits, the well development and testing, and then the consulting cost, the design and the construction management costs. So that gives us our well in the ground. Of course, we still need pump equipment. That's also part of the initial costs. So for that, we also have our contractor cost, pump and motor, materials. We have pipelines, valves, surface features, permits, and then the engineering, design, and construction management. This is the point where a lot of people are done. That's the only cost that they look at. Do cost comparison there and done. But these aren't the only costs that are incurred over a life cycle. During the life of a well, we also have future costs. They include operation and maintenance, such as the electrical energy or natural gas in some cases to remove that water from the earth. We have labor costs of the water purveyor's employees, turning valves, SCADA operators, etc. We have water quality issues, 3 general options when we don't meet whatever water quality standard that we're seeking. In the case of a drinking water system, potable water standard. So you can either treat the water, or we can blend it with a better quality well source or surface water source, or we can modify the well. So in any case, there's costs associated with those, and that might be needed to be addressed in the future. And then we have water production, maybe scale, accumulation, sand invasion, things like that. So there may be a need for such things as well cleaning. That's operations and maintenance. There's one other thing, aging infrastructure. So that relates to, of course, our pump and motor has to be replaced once in a while. The well itself only has a limited life. How often must it need to be replaced? Land costs can be a huge issue. When we do the economic analysis, because we want things to be apples and apples and not worry about different real estate costs, we're going to disregard that. But in the real world, maybe you replace a well with a second well at the same site, maybe a third well, maybe a fourth well. Pretty soon, you will need to acquire more land in what then may be a completely built out residential neighborhood where that extra acre of land is extraordinarily expensive. Sometimes in actual examples I'm aware of, well over $1 million for a vacant lot. It's an acre or half acre. So can be an issue. So let's start into this, starting with well design and installation overview. Now this is the way we typically do large production wells in Arizona, Southern California, where I've done most of my work. So that's usually flooded reverse, large diameter boreholes, typically 1,000 to 1,500 feet deep, sometimes much deeper, and typically cased to 16 to 18 inches in diameter. So pretty large, pretty deep. If it's different where you are, don't be discouraged or confused, because there's still a lot of this information that will be applicable, in my opinion, to everywhere in the world. So jumping into this, first thing we're going to do is design a well. And the human nature can be to design a well chronologically the way the well is installed. So a lot of times I hear new well designers considering what diameter they'll do and what depth for the surface casing and cement seal, etc., and work downward from there, from top to bottom. But I believe that the best approach philosophically on well design is to design from the inside out. That is to say, first consider the purpose of the well. Is it a monitoring well, dewatering well? Do you want it to be around for 5 years or 10 years over maybe some permit period? Or should it be there for as long as possible? What's that purpose? And that purpose will it be for 100 gallons per minute or 1,000 gallons per minute or 5,000 gallons per minute? That tells you the pump size, which in turn tells you the casing size. You can consider whether you're going to have any sounding tubes or gravel feed tubes in the annulus, which then tells you the borehole that you're going to have down this well. The drill bit that will be used to install this borehole will have to fit through that surface casing. So in fact, the surface casing is the last thing, not the first thing, that's designed in a well. That's all fine, but this is, when we write our technical specifications, we haven't gone out and collected any information yet. So we're not done designing. In the case of an engineering project like this building, the design's done, finished, and then the contractor comes along and builds it. But with a well, we need to be continuing to collect data as a basis for design as we go. So our process is to first put in our surface casing, put in our casing and put in a cement seal that of course protects the shallow subsurface in case there is a spill of contaminants in the future, meets regulatory mandates, and supports the heavy drilling equipment that's going to be parked around there. Then we drill a pilot hole, slightly smaller diameter. In the case of reverse flood, about 17.5 inches in diameter is typical, down to our total depth, and then we log the cuttings at about 10-foot intervals. So we know a good bit about the geology at this point, but we'd like to know more, so we bring in our geophysical logging van. Here it comes. They always move a little bit slow, but we get great information, so we don't mind. And we can see this is an example of an electric log, and of course, we don't have one log, we have a suite of different geophysical logs that we can compare against one another. So we get better information on the site-specific geology. For example, we have this example of this sand unit right here. Our geologist logged it as sand, 10 feet of sand, but we see from the E-log, we have 2 spikes of sand, so we now have better resolution on what our site-specific geology is. We haven't extrapolated it from nearby wells. We know it right there. But what we don't know is anything about our water quality or anything about our site-specific hydrology. In groundwater, we always have to keep in mind that little bit that we know and that mountain of stuff that we don't know. So we don't know that yet. We don't know the water quality, but moving forward here, we can install drill pipe with a cap at the bottom, with a perforated interval, typically 20, 25 feet long, and isolate it in an interval with a clay seal below and above it, pea gravel adjacent to it, like a temporary little well. So now we can purge groundwater. Remember, I think some of the previous talks you may have heard drilling with reverse flood. We can drill essentially with clear water. That means there's a lot of construction water percolates into the adjacent formation, so we need to purge that out before we grab a water sample. So we may purge for 12 hours in this case. If it was mud rotary, not so long. Doesn't matter. Either way, we take measures to be sure this is a representative, depth-specific water sample. And we'll do this between 5 and 10 times up the borehole. So we know the geology at this place. We know the depth-specific water quality at this place. We then measure a water level, so we know in this interval what the static water level is. And then we want to measure the hydrology, the hydraulic conductivity. Some folks use the term permeability. Either way, is this a good sponge or a bad sponge? Will water move through it readily or not? And we can determine that by putting a pressure transducer down that borehole. Pressure transducer, if you're not familiar with it, is just a fancy water level indicator that can measure water levels accurately and really fast, 1 measurement per second or so. As you see in the picture here, we can hook it up to a laptop computer. We have some very high-tech devices. We have a laptop computer, we have a pressure transducer, and we have a couple of buckets. Those buckets are the most valuable because we'll pour a couple of buckets of water in there and get a mound in our water table. As that moves out into the adjacent formation, we're doing what's called a slug test or a falling head test. And this is what the data looks like. You can see from this example, we poured in, not on purpose, slightly different heights of water in our we just do it twice for repeatability of data. It doesn't matter because we're measuring the slope of that drop. There's several mathematical equations that allow us to determine hydraulic conductivity. We use the Bauer-Rice, which was handy for us because we had Dr. Bauer and Mr. Rice available to develop this when we first started doing this in open boreholes. Now this is done all the time, falling head tests, by hydrogeologists in completed wells. In an open borehole, though, we have to remember what we know and what we don't know. And what we don't know is the exact, precise hydraulic conductivity. These are rough estimates because this is not a completed well. There's still a little bit of wall cake on that borehole face. That's okay, though, because it's a reasonable estimate, and the direction it would err on is being overly conservative. And if we're wrong, that's the way we'd like to be wrong. So we know that the hydraulic conductivity is at least this much and maybe more. So that's a good thing. Now we know the hydraulic conductivity estimate up and down the borehole, the water quality, and the geology. So now we have a lot of good information. We finalized our design at this point, and then remount our borehole to its final diameter, install our well casing and screen, filter pack, and cement seal. Voila, we have our well. But we're not done yet. Of course, we have to develop our well. And in well development, there has been, over decades, many debates over proper filter pack sizing, many debates over proper screen slot sizing. They're all fine, but what we cannot forget is the real bottleneck to water production is the wall cake, also known as skin damage. We have a hydraulic conductivity that's inherent to the aquifer. That's out here. If we get up to there, that's all we'll do. We'll never do better. Well, the filter pack is much larger than that hydraulic conductivity, and so is the screen. The wall cake is much lower than that. So that's the focus of development. Many ways to do development, and there's no correct answer to how one should do development. It varies from place to place as hydrogeology changes, as well usage changes, and so on. So some examples: swab and airlift, jetting, airlift open-ended, pump and surge, and then chemical treatment. And there's others. So for the areas where I work, we often use swab and airlift followed by pump and surge. That doesn't mean it's the best everywhere. It's certainly not the best everywhere. Other parts within Arizona will use horizontal jetting. It just depends on what we're doing. But in any case, in all these cases, what we want to do is have energy conveyed outward and also inward from the borehole so that we don't get sand bridging, so that when we shake material loose, we can convey it out of the well and break down that wall cake. So what we always talk about and what we'd like to do is have a good filter envelope where we remove the fines adjacent to the screen, we bring this coarse stuff in, and it looks like this, or so we think. I mean, that's what you see in the textbooks, and it's what, and I always try to draw that in my PowerPoint cartoons, but I've never been down there to know for sure. But if we have a scenario like is on the screen right now, we have nice graded filter pack envelope, but we've not removed a wall cake, we still have a limitation to production. So there may be times where the annulus is too wide. A narrower annulus, we may be able to get to it and break it down. Well, can't overdo this. If you have an inadequate filter pack envelope, you may have sand invasion, very bad. If you have too much filter pack, too much annulus width, you may not develop the well. So, and this may vary from place to place. So what I'm saying is ask yourself the question, focus on it, talk to your neighbors about what's done around you, and come up with the proper well design for your place in the world and for your well purpose. If you have a 100-gallon per minute well with the same screened interval as a 1,000-gallon per minute well, very different entrance velocities. That means this filter pack envelope needs to be adjusted accordingly. So let's talk now about materials that we might use in a well. As I said before, in Arizona where I'm working, we just can't use PVC wells because we're going deep, we're going large diameter. So looking at different types of steel, we have 3 common types. Good old low carbon steel, also known as mild steel or black steel. And this is the least expensive. It's also the least corrosion resistant of the 3. Then we have high strength, low alloy. Trade names include Corten and Kywell steel. If you've ever been to Pittsburgh and looked at the U.S. Steel building, that's HSLA. If you talk to old cable toolers, there's a lot of good old wells still out there made of hard red steel. And hard red steel is HSLA. It's red, it's oxidized because of the metallurgy. It tends to make, as I understand it, a protective coating of oxidized steel so that it reduces its tendency to corrode. I haven't seen a great amount of difference between scale accumulation of it and low carbon, but in corrosion resistance it seems to be greatly improved. And it costs a little more. Then of course we have stainless steel. 2 typical types of stainless steel, 316 and 304. For this presentation, for cost purposes, we're always talking about 304. So a little bit less costly, for less aggressive environments, but compared to the other 2, much more corrosion resistant and much more expensive, as you'll see. Now, we also need to consider scale accumulation. There can be pure mineral scale accumulation, like lime in the coffee pot, and that of course can be calcium carbonate. It can also be other minerals like gypsum, in some cases barite, etc. But that's not as pervasive in all locations as we have biochemical scale. These 2 photographs on the left and center are iron-related scale. On the right we have biofilm, slime. And so depending on the environment you're in, either of those can form. We can also have sulfate-reducing bacteria and other things. But it's important for us to recognize that these are not just mineral deposits. They are biochemical. They are formed by non-pathogenic bacteria that are in nature and that will come to the well and form these scale deposits as their homes, as they accumulate. There's a number of things we know about this bacteria. First off, they are naturally occurring and essentially ubiquitous. Naturally occurring and non-pathogenic. So we don't have to be afraid that the bacteria will make us sick. They will just clog off the aquifer. That's the problem with them. And they are on all continents of the earth. They have been found in the oil industry with drill stem tests to be at depths greater than 20,000 feet. So we're not going to go where they're not. They're out there. They're ubiquitous. Next thing we know is that a water well is a great place for them to thrive. You operate a water well, you're bringing water with its nutrients and dissolved oxygen, etc., from a great radius around there. So they just thrive there, and they just grow. These two are on a column pipe from a pump pulled from a well, but that same accumulation is happening inside the well. And this is actually a side view from a video. That's a well screen. You can't even see it because these accumulations can be substantial, as you'll see in some videos in a little bit here. The bacteria are growing interrelated colonies, so we can have little bubbles like this called tubercles, where we have iron-related scale on the outside. That likes an aerobic environment where we have some oxygen, dissolved oxygen in the water. Underneath it, the oxygen can't penetrate, so we have an anaerobic environment with no oxygen. So sulfate-reducing bacteria can accumulate down there. Sometimes we'll see a black stuff under a red bubble. That's what's going on. So we have interrelated colonies at each depth, and we can have different bacteria at different depths within a well. So the closer you look, the more complicated it gets. It's just important to recognize that, so if we're going to address it, we have some understanding of what we're fighting. Next, we need to keep in mind when we're cleaning wells that if we incompletely clean a well, the bacteria, the scale, will grow back faster than it did the first time. You often hear water system operators talk about a well that took 5 years to accumulate a certain amount of bacteria. They cleaned the well, that same amount grew back in 5 months. That's because they didn't do a thorough enough job in many cases. It's because if you have a rough surface, let's say you clean that scale but not all the way off. It wasn't nice smooth steel like the new well was. That rough surface gives a lot of surface area where the bacteria can return, grow back more rapidly than before, and create its home, its condominiums, which is the scale. So that's something that's important to consider for economic purposes, because that doesn't happen for free. And the last and most important is that the scale growth does not happen equally on all three of these steel types. We have an example of that. There's many of them I've seen in Arizona and some in Southern California, where neighboring wells very close to each other, just a few hundred feet apart, made of these different materials, show different amount of scale growth. But this is a well that I want to show you an example of, and it's unusual. It's in the El Paso, Texas area. It's unusual in that it's alternating stainless steel, low carbon steel, stainless steel, low carbon steel. So anywhere in this video that you see louvered well screen, it's made out of stainless steel. Anywhere where it's blank, it's made out of low carbon steel. And we'll see that there's a lot different accumulation of scale. So we go to the video link. And we're starting here at 166 feet. If you're not familiar with well videos, this is the light bar here in the middle. And we'll jump on down a little ways where we're below the water table. Now we can see a little bit of scale. These bumps are the tubercles I was talking about. We go a little bit further down and we'll come to a well screen, and we'll see that the scale accumulation is reduced. Here we're coming to the well screen, and you can see not quite as much. So I'll go down here a little further. And let me go back up a bit. When we go into this, you see a big difference. Different steel, different amount of scale growth. Bounce down a little bit further. Here we're back into the stainless steel again. And as we go from the stainless into the low carbon steel, big change in accumulation of steel. So this is at one place in Texas. Well, maybe you don't live at El Paso, Texas, but to varying orders of magnitude, we see this really all around. So very, very typical. And this is all the way to the bottom as we can just quickly bounce down. There's low carbon, stainless, low carbon, low carbon, and low carbon. So it just doesn't change. So this is important for us to realize, and we want to include this consideration in our economic analysis. Next, we'll go on to looking at the impact of hydraulic gradients on wells. So here's an animation of a cross-section, maybe a stream cut or a road cut. And we see what we have. This is meant to represent unconsolidated sediments, where we have maybe gravel, sand, silt, and they are in layers. We have stratigraphy. These are discontinuous lenses, so that's not uncommon. That means that water, groundwater, can move horizontally more readily than vertically, so it doesn't have to cross bedding planes. Kind of makes sense. But look a little closer within each sediment grain, or sediment unit, we see that the sediment grains themselves are not a bunch of little spheres. They are elongate. They're more like a frisbee or a dinner plate. Elongate because of the fractures on the rock surfaces, and when they're laid down by gravity or water, they are laid down in an imbricate fashion, like the shingles on a roof. And that means that groundwater can flow horizontally much easier than it can flow vertically. In fact, I put this picture in here to show you I'm not making this stuff up. We have, in fact, anisotropy. Anisotropy is a fancy word for a simple concept. It just means that it flows not the same in every direction. Horizontal versus vertical is quite different. Dr. Herman Bauer measured the differences in hydraulic conductivity in salt river gravels like this. Horizontal was 11 times greater than vertical, so an order of magnitude different. That is in coarse river run. If we get away from the river, it may be several orders of magnitude different. And that's not a bad thing, that's a good thing, because that means that we have a stratification of flow profiles, and we may be able to control the water quality and the water productivity of the well by understanding this. So it's a good thing for us. When we drill our pilot hole and we're testing it, sometimes we isolate an interval and we see that the water table of that interval is a little bit different than the regional water table. So as we do this many times up and down the hole, we may find that we have a situation like shown here that is a vertical hydraulic gradient. Shallower zones have higher water tables, deeper zones have lower water tables. This can be a downward gradient like we're showing here. It can also be an upward gradient in artesian areas, but it needs to be considered. Out here in the aquifer, the hydraulic gradient will be maintained by the stratigraphy and by the anisotropy in each unit. But when we install a well, we've connected the dots. So water will flow from high pressure to low pressure, and we'll have cross communication inside the well. Does this matter? It does. It should be a component of well design, because if I designed this well for you and I sold this to you today, I might say, well, the concentration of nitrate is just a little bit over drinking water standards, but don't you worry, because it's non-detect in all these others. And we'll do a pumping test tomorrow, and we do. We grab a water sample that's completely potable. But that's not a good well design, because then as a water system operator, you may operate it until the fall of the year, and it's out of service because of low water demand for a month or two or three. What happens in the springtime when you turn it on? You get high nitrate everywhere. And it may take a long time to pump that off, and it would need to be pumped to waste, which might be very expensive too. So that's not a good well design. This sort of hydraulic gradient should be considered. It's an economic consideration. That's under non-pumping conditions. What about under pumping conditions? Well, we turn on the pump, we get a drawdown cone. And Darcy's law tells us about that pumping. It's only controlled by three variables, generally. Hydraulic conductivity, which is inherent to the various strata, and cross-sectional area, which in a well is the same from top to bottom, and gradient. So the gradient in a pumping well is the difference between the static water level and the pumping water level. That's the driving force that pushes the molecules of water from outside the well into it. So the upper two units we have here are going to produce water because their static water level is higher than the pumping water level. But what about this third unit that has a static water level almost the same as the pumping water level? That's not going to make a drop of water, because even if we take a very large hydraulic conductivity multiplied by a very large cross-sectional area multiplied by 0, we're not going to get a drop of water. So it doesn't matter. That means that there's no asset there. It's an extreme scenario, but we may even have intervals with a static water level lower than the pumping water level. That's counterintuitive, but I'll show you an example. It can exist, and it should be considered, even though it's extreme, because this well is an asset from here up and a liability from here down. So the money that was paid for this well from this point down was thrown away. And in fact, liability has been introduced to the well owner because of the cross communication. I'll show you these examples with a video, and I just want to be sure in case anybody's not looked at well videos. There'll be two lenses. There's a downward lens like you saw in that earlier video, and there's the light bar. And there's also a sideways lens that can spin around. So don't want you to be oriented. We can be looking sideways or we can be looking downward. And the first video is of bar holes. I see a show of hands. Who's heard of or seen bar holes before? Just a few of you? Well, that's good. Bar holes are not good. They're not a good idea. They're an example of when a driller would rather not use casing clamps, and so they'll cut big 2 or 3 inch holes, run a bar through them, and use them with cable loops to install his well. This might be handy for the driller, but it also allows water and sand and such to come in. And so I'm going to show you a video of a well that has a scenario like this. Bar holes were installed every 40 feet, so that was the length of the casing sections. And we have a hydraulic gradient. But what we're going to be able to see in this video is water flowing in at different rates in response to this hydraulic gradient. So we're actually going to look at a hydraulic gradient under non-pumping conditions here. First, we'll see some cascading water. That's going to be perched above the regional water table. That's a pretty bad thing. That can cause some aeration, will damage pumps. Can be some poor quality water coming in there. So that's bad to start with. But even if we disregard that, of course, that's a perched aquifer. It might be a little bit different. We will see from across the next 80 feet here, 3 different bar holes, parted 40 feet from one another, that show substantially different pressure heads. So we have a water table we'll be coming to here shortly. There it is. And our water table is on the inside of the well. We have a different water pressure on the outside of the well. So we'll peel down here to 430 feet where we'll see a strong inflow of water. We'll see that inflow pretty clearly because it's bringing sand with it. Another bad thing for this well. Pretty strong flow coming in. Now that flow is in response to the water table outside the well casing is that much higher than where it is on the inside because that interval is feeling a different hydraulic pressure. So if we go down 40 feet to the next set of bar holes, that's at 470. Really not that great a distance, maybe a little more than from me to the wall. But even that relatively short distance, we see that we've gone from a high flow down to a medium flow. So once he dips the light in there, you'll see he's just sort of coming in at a moderate speed. Not nearly so much. So now we'll go down 40 more feet. That'll take us down to 510 feet. And at that depth, we will see no flow coming in at all. Now these little white specks you see are sand-sized floating debris. If you keep your eye on the left-hand side, it turns out that the casing, the centralizer on the camera will shake loose some very fine material, and so that's a little more convincing that there is in fact no flow coming in from this last interval. So, all right, here's a pop quiz. The video ends here. We've seen strong flow, medium flow, no flow. If we went 40 more feet and looked at the next set of bar holes, what would we see? Outflow, absolutely. There's no magic. We're either going to fill up the well or it will be outflow. So we have exactly the scenario that I indicated. We have cross communication. So that's with this well. Now let's look at the pumping condition. You know, I described this somewhat incredible scenario where we're pumping and yet water is going out the bottom. Well, the video I'm going to show you is pumping. So we have a pump and we have an open-ended access tube adjacent to it. It's pumping, in fact, at 2,300 gallons per minute, a pretty good flow. And the place that is the flowing upward versus flowing downward depth is about 600 feet. I'll tell you that so you can kind of be watching for it. Now I'm going to briefly pause this to be sure you're oriented. This is the access tube. This is the side of the column pipe. The water's coming out there, 2,300 gallons per minute, little sounding tube. This is the light bars, and then there's the tube through which this camera will be going through, this access tube. Incredibly boring going through this access tube, so I will spare you that. We will go down to the bottom. Here we're at 516 feet, just at the bottom of the access tube, and you can see why this video is being done. Lots of sand. Sand's a very bad thing, but we don't mind it because it's not our well, for one thing, and it's allowing us to see which way the water's flowing. So we'll go down a little bit further where I believe there's a side view, and I want you to make a mental note of that side view. That's what it looks like when 2,300 gallons per minute are going to a pump intake. So we can compare that upward flow of sand to what we may see deeper down to see if it continues to flow upward at greater depth. So we'll go down a little further here. This is where it almost hits the wall. Whoa, not quite. Here we're at 584. Just sort of swirling around now already. 588. 598, starting to go downward here. 605. Starting to look like it's snowing. So we have water flowing both directions. Spinner logging in this well confirmed this more quantitatively. I just don't have that information. And so we have, in fact, a well here that is producing not a drop of water, and it's flowing down even at 2,300 gallons per minute. It can happen. So what if we weren't having outflow? The difference between here and here may reduce the amount of productivity, and that's something that just should be considered because it's what we're paying energy dollars for. So let's consider, we've talked up till now about what we could do in a new well we might install. What about wells we already own? Can we take a look at those, or may inherit as we expand our area? So there's well reconstruction, well rehabilitation. To do that, again, we want to have a basis for that. We have this is the setup we just saw in the video, where we have a submersible pump and an access tube beside it. We can turn it on and get a drawdown cone. And so this is the setup at the land surface, where we have usually a plastic access tube. We have a little sounding tube. I think it's right there, electrical cable going down. So we bring in our logger again. This time he has a spinner log. That's not like the geophysical logs that are looking at the geologic information. This has a tool on the end of the wire line that is similar with impellers to a flow meter you might have in a regular pipeline. So that gives an indication of what the flow is, and as it's passed at a constant rate of speed down the well, the water flowing against it is reduced when it gets under a pay zone, and reduced again until it gets down to zero. So through that, we can know the gallons per minute coming in. So in one day, we can collect a lot of information. First, we can do a constant rate pumping test at this well. Maybe only 8 hours or so. Still, it's site-specific data, not brought in from neighboring wells. Next, we can do this dynamic, which is to say pumping, spinner log. So we can know the gallons per minute that come in at each depth. The last thing, we can collect a depth-specific sample with our tool here, just a stainless steel barrel, pull a little vacuum into it with a vacuum pump, and grab a depth-specific sample. Now, of course, each sample represents from that interval to the bottom. There's no seals or packers or anything here, but we can do a mass balance analysis, do a little math, and figure out what the production of both quantity and quality is at each depth. So we got pretty good information. Now we can do whatever we need to do to modify the well structure, improve the water quality, consider what the water quantity will be like. Whatever fix we need, we have information as a basis to look at that. Another way we can collect the same information is with a dye tracer. Just another way to do a flow profile. That's done with a little trailer. This is actually a technique developed by the U.S. Geological Survey, where there's a trailer with two spools. One has got, this is little ductile tubing about the size of this laser pointer that can be sometimes installed without removing the existing pump, down to some depth where we put off a little squirt, a small amount of rhodamine red dye. Now that's NSF approved, so we can even put it into drinking water systems. when I first heard about this, I thought, red water coming out the discharge pipe, women screaming, children's crying, no. But it's not like that. You will never see the red coming out. This is a small amount that is never seen at the land surface, but it's highly fluorescent. So with a fluorometer, that's one of these devices here, it can be measured down to the part per billion level. So just a little bit can be measured very readily, very accurately at the land surface. And that makes it neat, so we can do squirts at different depths and do the same thing. With our other spool here, we can use a gas displacement pump to grab our water sample. So we're getting the same information, just in a different way. So these can be used, two different tools for the toolbox, to characterize a well so that we can fix it. It's just a nice thing to keep in mind. Now we have the background. We're ready to look into our life cycle economic analysis. Again, maybe some of this stuff might be different than what you do in your area, but the economic analysis, the fundamentals of it really are useful to apply in any hydrogeological environment. Why do we care about economic analysis? Well, you see a lot of water flowing out of the pipe here. What there's also a lot of is dollars flowing out of that pipeline in the form of energy dollars. This is 3,300 gallons per minute, which is being pumped from greater than 400 feet. There's a lot of energy being, somewhere there's an electric meter spinning very fast when this is pumping. And we have a formula that describes this. I'm showing one of many sources. There's a lot of different sources for how we can calculate this. And we have our energy cost per hour multiplied or equals gallons per minute times total dynamic head, that's feet of lift, times a constant times our electrical cost, typically around 10 cents per kilowatt hour, divided by a constant times the pump and motor efficiency. And these are typical ranges for new equipment. So does this energy cost make a difference? Does it make any difference at all? Is it just negligible? Well, if you do the math and you assume that there's a typical well, say 1,000 gallons per minute, and you don't design it properly, or you don't develop it fully, and you have to lift that water an extra 100 feet, and you operate that well for a year, and you operate it at a typical municipal water pumping duty. So say it's on 70% of the time, and you apply all that. What you find is that just under $17,000 per year is what you're paying. $17,000 is a lot, even for a large entity. And that's not counting wear and tear on pump and motors and all kinds of other things that are exacerbating the cost. It's just electrical cost. So it's substantial. And when we do the economic analysis, we find that this is one of the biggest ticket items, is the energy cost. So we want to be very focused on it. So what about wellhead treatment? Is water quality an issue? Well, sometimes infrastructure to treat water is already in place, other times it's not. So a nice, fair, conservative way is to look not at construction cost, installation cost of wellhead treatment, but just operation and maintenance cost. Let's say it's already in place. How much does it cost to do that? So I got information on comparable situations where there is wellhead treatment, so we can look at that compared to modifying a well. So these are just operations costs. Many different ways to treat water. One is coagulation, filtration. So if we can backwash that to the sewer, it costs us about $8,000 a month. And this is for a 3,000 gallon per minute system. So we could even divide that by 3 and say, yeah, about $2,600 a month. If we can't do that though, if we can't put it in the sewer, then it goes up to, dividing by 3, about $10,000 per month. Well, what about if we have some arsenic? We sure have that in Arizona quite a bit. Arsenic treatment with absorptive media, about $25,000 dividing by 3 per month. And if we have it without pH adjustment, that means that the construction cost was higher, then it goes up by a little bit. What about granular activated carbon, GAC? This is for 1,000 gallon per minute. This would not be, we can't divide this by 3. That's $100,000 a month. Ooh, starting to get up there. And if we use membrane treatment, there's electrodialysis reversal and there's reverse osmosis. The technology has really improved on this recently, but it's still kind of pricey. If we can put it in the sewer, it's $26,000 a month. If we cannot do that, it goes way up, around $105,000 a month. So we have quite a bit of cost even every month that we're incurring. All right, comparing that with the well fixes that we just looked at, spinner log and dye tracer log. Well, if we look at the analyses, they vary from well to well, generally $10,000 to $80,000. Typical numbers, I'd say around $30,000. To do fixes, a lot of different kinds of ways to fix a well, and they vary from $50,000 to $400,000. And I'd say typical numbers are $150,000 to $200,000. That means in many of these cases, you may get a payback in months or a few years. So, and that's just O&M costs. We haven't even looked at construction costs. So this can be, but you know, this doesn't work. This well reconstruction does not work every time, but the evaluation will tell you whether it's going to work before you've spent all that money. So it's prudent to take a look at it, yet it's so often not done. It seems like an unfortunate economic element out there. So going to our economic analysis, we have Arizona here, where this is based in. May not be the same as what you'd have in your state. If you wanted to heavily rely on an economic analysis, I strongly rely you do one in your service area. But for this, we, as I mentioned before, we took a look backward in time, and we took a look forward in time. So the backward in time look is the time series analysis. What we did was we got information from 70 wells. These are actual low bids from actual jobs that were actually drilled. And they're mostly in Phoenix, but spread all around the state. And these represent 8 different drilling companies and 5 different hydrogeology consultants. So they weren't all work that I worked on, but information I was able to acquire. And they represent a pretty broad stretch of time from 1993 to this year. So 18 years. And if we think about how that time period has changed economically, we've gone from pre-boom to development boom in Arizona to development bust in Arizona. So we've kind of have both sides of the hill represented by this time period. So we'll take a look at all that. That's the look back in time, but we also have to have a look forward in time, and that's our life cycle economic analysis. This is where we'll look at our 3 different steel types and see which one is worth the money to us. For that, we will average O&M costs from their actual numbers provided by the city of Phoenix, and we will use current as possible information from drilling bids and from suppliers to look at costs going into the future. So let's start with casing costs. We're now looking back in time. I want to caution you that the time scale here is not real linear. When I did this originally in PowerPoint, the formatting was such that it accommodated how many bars, how much information was between each year. So you notice that the difference between 2001 and 2002 is not the same as between 2002 and 2003. So you got to actually read the numbers. So go ahead and do that whenever the time suits you. So for 16-inch and 18-inch, to get a better data set, we lump those two together. We look at, if you can see the colors here, blue is low carbon steel, red is high strength low alloy, and green is stainless steel. So casing costs, these are dollars per linear foot. First, we have low carbon steel. In the earlier days, before about 2002, we used low carbon way more often. But we see that it stayed around, looks like about 25, maybe got up to $50 per foot. And then after about 2004 or 5, it shot up to about $75 per linear foot. Then we have high strength low alloy. That began being used in 2001, 2, 3, a little bit more, and had a cost of around $75, jumped up to about maybe $125 per linear foot. That increase again being about 2005. Then we have stainless steel, just a little bit more expensive. Started out around maybe $225 per linear foot up until around 2005 or 6, and then jumped up to $375 per linear foot. Now in all these cases, around 2005, 2006, there's an increase. That's not too mysterious. That's when, if you recall, great amount of development in China, other places around the world, using a lot of material. The price of steels, all these steels, went up at that time. That's what caused that, but we see that clearly shown here in the cost of material in this time series. What if we look at filter pack sand? That's a little different. This is for CARMU's, Colorado Silica Sand, and I just have a long record of that, and it's what we typically use for drinking water wells in the Southwest. And so, big jump in the early days, about 2000, and a slow, gradual increase with and these different colors are different grain sizes. Coarsest is 4.8 at the top, 6.9 is the red in the middle, and this is 8.12. These are just typical filter pack sizes. And of course, this is quarried sand. It's not manufactured, not truly manufactured, and so it is more rare to get coarser, windblown sand. So it's not too surprising that the coarser you go, the higher the cost. Well, that 4.8 became unavailable about 2004 or so. 6.9 and 8.12 have leveled off in recent years, but don't know if that'll stay the trend or they'll be going back up. But this is what we see from about 2000 when I first started getting information up until now, 2011. Here's cement. Cement was pretty steady, slightly increasing up until about 2005 and then had a jump. Now getting up to on the range of about $400, that's per cubic yard. And these are from, if you can notice the source here, this is information that's actually from the bids. So this includes all supplying at the site, installation, contractor markup, everything. This is at the site. And then we wanted costs for non-expendables. How much does labor and fuel cost? How can we estimate that? The best way I could guess was looking at just drilling, like pilot hole costs per linear foot, and standby costs, the cost of the rig and the crew. So we looked at those two. The blue is the pilot hole, slightly gradually increasing. There's noise in the data, but it seems to have increased most of the jump up here till about 2005, then fairly steady. I don't know the reason for this decline in return of the standby time, and again, some noise in the data, but there again seems to be an increase in about 2005 for standby time. I don't know if that's related to more work going on, so there was opportunity to get, I think drillers for a long time didn't increase their costs enough. That could have been an economic adjustment of that sort, or it could have been fuel costs, I'm not sure. So we want to look at the whole well costs. And we have different wells of different depths and slightly different diameters. So what we can do is normalize that with this little equation down here and look at unit costs. This is what engineers call diameter inch foot cost, where we have the total well cost and we divide that by the inches of diameter times the feet of depth. And that makes it to where we can compare everything as apples to apples. And so with this, we can look at our low carbon steel, our high strength low alloy, and our stainless steel. The only problem with this is we don't really know what's these units mean. Is $15 a lot or not very much? Well, now we can normalize this. We're prepared to normalize it to a depth, and the one that we're going to use when we look forward in time is going to be 18 inches in diameter and 1,200 feet deep. The reason for that is because when these economic analyses were done, and they were done multiple times, that was the typical depth and diameter that the water purveyors were using. So to make this an 18-inch diameter, 1,200 foot depth well, we just do the math here and apply this for each well. So we see that low carbon steel over this time period, if we drilled an 18-inch diameter, 1,200 foot depth well in the year 2000, it would be, looks like about $300,000 or so, right in here, going up and up and in time. More recently, maybe $400,000, maybe $500,000 now for a well that deep. So that's what we're saying with this graph. Looking at the same for HSLA, we see that HSLA started at about 400,000 or so, has kind of hiked up since 2005, where now we're looking at a little over 600,000 for a well of that depth and diameter. Stainless steel started as kind of a good deal if you bought your well back in these days and had stainless steel, but more recently, maybe 750, 800, maybe up to $1 million for a 1,200 foot deep, 18-inch diameter stainless steel well. So this is the cost that we're seeing up until now, having looked back in time. The main thing that jumps out is these adjustments just due to material costs in 2005. But now let's look forward in time. Looking forward in time, we want to compare 3 different wells. Because of economics, oftentimes the water providers will want to go low carbon steel above the perforated interval and just have a dissimilar metal connector where needed. It would be needed with stainless steel. It would not be needed with HSLA or low carbon, because to avoid galvanic corrosion where dissimilar metals touch each other. So this is the scenario that we're going to compare, where we only change the screen metal type. Everything else is the same in these wells. These wells are 1,200 feet deep, 18 inches in diameter. We have a 400-foot water table, and we have 500 feet of screen, and it's louvered screen. We had a lot of good information on all these things, and they were typical situations, so this is the comparison that we did. So we have to make a lot of assumptions for all these wells. One of them would be that we're going to look at a 75-year life cycle. We're not going to look at the initial cost. We're going to look at future costs out to 75 years. Each of the wells will pump at 1,200 gallons per minute, and they will be used 65% of the time. These are real City of Phoenix numbers. Specific capacity, the first day we put them in, is 20 gallons per minute per foot of drawdown. And the water table is at 400 feet, and there's a regional drawdown, 3 feet per year. That's kind of bad, that's a lot. So the regional water table drops every year, 3 feet. But it was happening in some of the more extreme scenarios. We thought it would be good to apply, but we're applying it to all 3, so that's fine. Then we're going to say that we're not just pumping it out at the land surface, we're pumping it into a pipeline or up the hill to a reservoir, and so we're going to add another 22 PSI, which is 50 feet of lift. So we're going to add that all to it, and we're going to say the energy cost 8 cents per kilowatt hour. Real numbers for this scenario. Our pumps, when they're new, are in the median of the range that I listed before. 78% efficiency for pumps, 87% efficiency for motors, and each of them are replaced every 10 years. The new wells won't need a pump, but after 10 years, everything has to be replaced. So we're applying all these assumptions to all 3, but they have differences between one another. So we'll look at the low carbon steel first, and we're going to say that gets some scale growth over the years, and we're going to say that after every 5 years, it gets enough scale that its efficiency goes down, which is to say its specific capacity goes down by 25%. So we clean it, and it comes back, but not quite all the way. If anybody saw the talk that Kevin McGinnis did yesterday on well rehabilitation, it gave an example, an actual example of where a well's cleaned, came back part way. Wells cleaned, came back part way. Well, we see that in many wells. So to apply a typical amount to that, we say that after we clean it, it has an 88% recovery, not 100%, just part way. And this well lasts 25 years. After that, it's corroded. We have to replace it. And when we replace it at the same site with a new well, then that new well is 40% better than the specific capacity wherever we left off. It improves by 40%. So that's what we're saying for low carbon steel. For HSLA, a little bit better. Here we have 25% loss, but it doesn't happen in 5 years, it happens in 6 years. When we clean it, it doesn't get 88% better, it gets 90%, just almost as good as it was, but not quite. It lasts a lot longer though, that's the big deal with HSLA. 40 years instead of 25. Also, when we replace it, it goes 40% better than the specific capacity where we left off. Stainless steel, now this, as you saw in the video, it doesn't scale so much. So we're going to say that it loses 25%, but after 30 years. And it will be, when we clean it, it'll get even a little bit better, 95%. But we will assume that every time we clean it, we never brush it. It's always acidized, which costs more. We're only going to clean it less often, so that's okay. And then it will last its full 75 years. So we don't have to replace this during this 75-year life cycle. So that's all our assumptions, okay? I'll show you these specific capacities graphically so it's not confusing. So here's a chart of time, 75 years, versus specific capacity. We start at 20, and here's low carbon steel. After 5 years, it's lost 1, 2, 3, 4, 5. It's lost 20%, 25%, so it's down from 20 all the way to 15 gallons per minute per foot. Then we clean it, and it goes down, clean it, goes down, clean it, goes down. This is the full 25-year life cycle. So to be clear, when we have a specific capacity at one point in time and it goes down from there and we clean it, it doesn't go 100% better, it goes 88%. So we're measuring from the bottom up. So I don't want to mislead you on how this is measured. Once the well has ended its useful life, we replace it and it's improved by 40%. That's to say, wherever we left off, the specific capacity, it's improved by 40%, but it's not as good as where it started. Again, that's a real-world observation, so we applied that. So the life cycle in the low carbon looks like this. We have 3 wells, each lasting 25 years. HSLA, a little bit better. We can see we go all the way to a 40-year before we have to replace it, and it's a little bit better throughout. So we have a little better situation. The stainless steel doesn't have to be cleaned nearly as often, and the same well lasts all the way through. So this is what we'll use for our comparison in terms of our energy use. Now these 3 wells, we came up with as good of numbers as we could. We took labor costs, drilling costs, things like that from the last 5 years. So we had 12 different low bid actual construction costs for expendables, rope, dope, and soap, bits, things like that, and unit costs, not counting screen and such. The screen and casing, we got 2011 numbers and added contractor markups to it. So it was very real world. This is the numbers, and we did not include replacing land. So this is the real world numbers. For low carbon, we have 512,000 rough numbers. For HSLA, about 567,000. And for stainless steel, we have 776,000. That's more expensive by a lot. Is it worth it? That's the question we're addressing. So we can look at all the elements of the life cycle, and there are many. We have low carbon on the left, HSLA in the middle, and stainless steel on the right. The first thing we'll consider for all 3 is the well installation itself. We have the numbers as I listed. Happens 3 times for low carbon, twice for HSLA, and once for stainless steel. Then we have additional well construction costs. So sound abatement from our last 5 years bids, our actual bids, we see the typical bid amount is $65 per linear foot. And what we usually require is 250 feet or so of sound blankets. That's because we have to drill in neighborhoods. If we drill too far from a neighborhood, there's complaints about why do we have this long pipeline. If we drill right by the neighborhood, we have complaints about noise. It is a 24/7 issue, so we do sound abatement and get a public relations subconsultant, which is not in here. And then there's fluid disposal. Kind of a high number, but for the city of Phoenix, that's real numbers. Those were actually provided numbers, so disposing of fluid can be very pricey, $15,000 per well. We have demolition of existing infrastructure, like storage tanks and valving, et cetera. That can be very pricey. Actual numbers from the city of Phoenix, $25,000 per well. And then re-equipping the site with SCADA, chlorination, et cetera, $200,000 per site. Again, information from the city of Phoenix. That all adds up, and times 3 wells, we have $256,000 per well, and that happens times 3 wells, 2 wells, and 1 well for each across. Then we have our consulting costs, one of my favorites, and we did not use what is actually typically needed for the city of Phoenix. There's a lot of extra considerations, a little bit more than this. So we dropped it to what I consider to be a typical well design and construction management cost, $70,000 for the hydrogeologist. For the engineering, the numbers that I was given for both design and construction management, $400,000. So we applied that to 3 wells, 2 wells, and 1 well, okay? Then there's operations and maintenance. So we have to clean these wells periodically, as shown on the graphs. Well, to acidize a well and disposal of that acid, around $100,000. So we have to do that 6 times for these 2 wells and twice here. For brushing and baling, and we were doing that for the HSLA and low carbon steel well alternately. Acidize 1 time, the next 5 or 6 years, brush and bale. Acidize, brush and bale. so alternately. And we're saying about $40,000 there. That's $20,000 to push and pull the pump and $20,000 for the brush and bale. And that's based on, I think that was about $300 per hour for typically a cable tool or pump rig to do that. That's what that was based on. And then there's the labor of the actual water purveyor, whether it's a private water company or a municipality. There are guys we assume to be $60 an hour. That's what the city of Phoenix provided to us. And 600 hours a year, that's about 11 hours a week. We didn't apply that for the first year of a new well. So we have slightly different numbers here, 72 years, 73, and 74 years. So then we have motor replacement. That happens every 10 years and costs $25,000. And we have pump replacement. That happens every 10 years. We're using the number 78,000, about 70,000 for the pump, and there might be column pipe replacement, things like that. So we put in another 8,000 there. So and we applied these by the amount of times. With the replacement of pumps, there's slight differences here, 9, 8, and 8, 9, 8, and 8. And the last one is the electrical cost, and the biggest one. And this just reflects doing that math, the formula you saw before, times the varying specific capacities. So when we plug all this into a rather large spreadsheet, what we come up with is for a low carbon steel well over 75 years, total cost $15.7 million, for HSLA $14.5 million, and for stainless steel $12.4 million. Now these costs aren't incurred evenly every year of the 75 years, but if we do the math simply and we just divide by 75, we can say the annual cost is about $210,000, $193,000, $166,000. And that means that compared to stainless steel, you paid about $3.3 million more over 75 years for the low carbon steel, and you paid over $2 million more for the HSLA. That would be about $44,000 per year or $28,000 per year. That means that if we do look at it evenly for all 75 years, the payback for HSLA, stainless steel versus HSLA, would be about 7.5 years. And for low carbon steel would be about 6 years. So interestingly, I've not done this just once. A lot of people like to say, this isn't my first rodeo. I say, this isn't my first life cycle economic analysis. And I've done this in 2003 for a large water company, looking at 36 wells. And we came up with 5.8 years to pay back stainless steel versus low carbon. Did it again for the city of Phoenix, looking at 68 wells, 5.7 years, low carbon steel versus stainless steel. And then this year, updating to current and looking at 70 wells, right at 6. So 6.0, 5.7, 5.8, round numbers, it's 6 years. What's interesting is, no matter how the economy varies, the answer is the same. If you look at a life cycle, it's the same for a large system in Arizona. In your area, it may be different depending on needs and variability, but I think there are some takeaways that are universal. The first for us is well installation costs increased in 2005. I think that's global. For the 3 analyses that I did, I saw the same answer essentially all 3 times. For stainless steel in Arizona, you can get about a 6-year payback that may be represented by over $3 million over that 75-year period. And the most important, that's global everywhere, is you should not just look at those initial costs. You should look at the life cycle costs throughout the life of that well. Even if if you don't need this well for 75 years, if you have a power plant that's going to be obsolete in 20 years, fine. Look at a 20-year life cycle. But that life cycle planning is appropriate for every water well that we install. And this message, I don't want to just be preaching to the choir, really should be conveyed to the owners of wells. They're the ones with the pocketbooks that should be making these decisions, and it's just good economic sense. With that, I'll be glad to answer any questions you may have, but before I do, I want to again extend appreciation to the National Groundwater Association. They are a 501c3 nonprofit organization, so your your contribution to them is tax deductible, and you can contact them at this website or at those phone numbers. With that, I again appreciate very much the opportunity to be the McEllhiney Lecturer this year, and would be glad to field any questions that you may have. Yes.
Did you look at what the savings was essentially by a cost per acre foot? So the total pumping over the 75 years, and what that ultimately came down to?
So the question is, did we look at the cost per acre foot savings? And no, we did not. I think, though, it would be the same answer because we assumed that all 3 wells pumped at the same water duty and pumped at 1,200 gallons per minute. They just use different amounts of energy to do so. Yes.
When you had 2 different metals, Dave here.
Yes.
When you had 2 different metals, you mentioned a connector between the 2, so you'd build up a charge, anode and cathode. But even with that connector, could you build up a charge between 2 different metals in the well, and would that affect the scaling that we saw in your downhole video?
I am not sure. I know that corrosion is greatly impacted by stray currents sometimes, and so the question is with the dissimilar metals, even with a dissimilar metal connector that may avoid or prevent corrosion at that point, could there be different scale accumulations? Is that correct?
Yes.
And I don't know. That's a good question. I don't know the answer to that. I think there's that would be something to keep an eye on. What is of interest, if you remember the first video, there was a lot of difference in scale. And of course, the less noble steel will be the low carbon steel. That's what will corrode. Didn't see any corrosion. That well was installed in 1955, and I'm guessing that it was just metal to metal welded together. I was surprised I didn't see any corrosion, but it may be the scale's holding it together. I don't know.
Were you using, on the stainless steel wells, were you using the whole length of the well in stainless steel or just the screen?
Just the screen interval like shown in the cartoon. So it was low carbon steel above, but the entire screened interval was stainless. Yeah. Now this is current dollars. You know, I've had MBA folks ask me, why didn't I amortize it and bring it back to current and all these things? Well, one reason is that's just real economic, and I'm a hydrogeologist. I can't do that. But the other thing is, in asking people who know more about economics than I do, is for comparison of planning purposes, this is appropriate because if we did use future dollars, then in the future, let's say in the case of low carbon steel, we borrow money to put in a well today. We do it again in 25 years. We do it again in 50 years. That future money is more expensive than today's money. So actually, this is conservative, and it's a good way to do planning is on today's dollars, current dollar analysis. So that's what this is. Any other questions? Yes, sir.
On the case where you had the flow in the lower part of the well not participating in the production,
Yes?
what are the implications for determining transmissivity in an aquifer test? And do you, let's say you had that interface halfway down the well screen, you'd be off for transmissivity by a factor of 2. Would you think that you would need to do some spinner logs prior to doing an aquifer pumping test to get an accurate interpretation? Do you go that far in recommendation?
I don't think I would go that far always, but let me repeat the question because that was an excellent question. I showed you a well where, due to a hydraulic gradient, only part of the well was producing any water at all. So when we do an aquifer test and we determine a transmissivity, the Tice equation assumes a lot of things that don't happen, but including our aquifer thickness. We usually apply not all the way up to the water table unless we have complete penetration, but we'll do our screened interval. So in this example, we had 700 or 800 foot screened interval with about half of that contributing water. So we would misinterpret, if we just did a pumping test without any of the spinner log data, we would misinterpret that transmissivity. I think that probably happens in the real world, because if the spinner data weren't apparent, if we did not know this, how would we, do we go and spinner log every well that we've installed, and do we do that to every well that we've ever tested? No, we don't. Usually we're going to have a hard time talking anybody into paying us to do that, is one reason. The analysis does cost some money, but could it impact things? Yes, it might. So if you had a very critical bit of information you wanted to collect, a flow profile is appropriate. Here's something I've noticed that's less expensive, just something to keep in mind. If you're ever looking at a well video and you see floating particles that are convecting, I often consider that to indicate or suggest, shall we say, vertical flow. You don't know if it's upward or downward, but if there's water flowing like this, and sometimes you see that, you might want to say, why don't we spinner log this well? Or do a dye tracer. But determine the flow profile, see if it's going up or down, because it might be. And that might change how you want to further evaluate it or use it. So there's all kinds of, it's complicated out there in nature. It's also not of infinite areal extent and isotropic and homogeneous. But, yes, sir?
Marvin, being an old guy, we used to do that kind of the easy way by just putting some surveyor tape on the camera, and you can see by which you stop the camera and it'll tell you which way it's flowing.
Right.
There's no quantification, but it will tell
That,
you the direction.
you can put surveyor tape, you can put a little ribbon and see which way it's flapping. Yeah. Old school is pretty good sometimes. There's a lot of good lessons I've learned from talking to old drillers. Some of them aren't doable anymore. They're not acceptable within our health and safety and regulatory limits. But a lot of them provide great information.
We did use non-Chinese.
Yeah. Yeah. Any other questions? Yes, sir.
So, old-time driller, so I'm going to ask a question that probably everybody in the room knows, but I'm curious. So if a well is moving, so this water moves downward whether you're pumping it or not, right?
Right.
So the well will be, in my mind, from what you're showing me, without a lot of technical knowledge, if you stop and plug the bottom half of that well, the well would produce more because that water going down is a loss from the upper aquifers. Is that correct?
No, it's actually, in theory, it would produce the same. If you plugged it to, say, 600 feet, then the water that you're getting now, you're still going to get it. You just sealed off the water that's going to go downward. So you've gone down to where the static water level is exactly the same as your pumping water level, but you've gotten rid of the stuff that's below you. But the stuff that's above, 1 inch above static, it's not making much water. So the only way to get more of that water is to pump harder and get your drawdown greater. And what I didn't mention, but also keep in mind, is the drawdown inside the well, if it's not completely developed, may not be the same as the drawdown just outside the well. So that's really, it's the true pumping water level versus the true static water level that are what you have to compare. Yes.
What about the losses over time of filling from sand and all this particulate matter from bacteria wear on your pumps, and that has an effect too, isn't it? Another factor to consider and
That's a good question. The question was, what about the wear and tear on pumps from sand invasion, etc.? That means that the pump will be less efficient over time. We made an assumption that the pumps will have a certain efficiency. We held that constant through time. So there's going to be losses there. And so, and really, if you're going to try to make it real world, the more losses of specific capacity means the less, probably the more clogging. The more clogging means the higher entrance velocities. The higher entrance velocities mean more sand invasions, means more wear and tear on the pumps. So in the real world, when you lose From the energy side, you directly and immediately begin to lose on the pump side usually. It wears and tears on it. So that was not included in this. So we're not even as extreme as before. Still got the same answer. I guess I just didn't, I ran out of patience messing with this. What was, I swear to you, a massive spreadsheet. When you put 50 wells in, or 70, but it was a big one. Yes, sir.
Just curious about would it make economic sense to increase the pumping water level in that well in order to capture what's being lost in the lower formation?
The question is, would it make sense to increase the pumping water level to capture that lower formation? If you wanted to stop cross-contamination, you could do that. But you got to turn it off once in a while. That means you got to pump more water out, unless you start drying upstream, which we didn't see happening. We went through the access tube past the static water level, so we don't know where that was. That's not a well I worked on or designed. That was just a well that I was provided the video, and so that that would probably not be the good solution. That is an extreme case where there's really there's got to be tens of feet of hydraulic gradient. And so that would be something where the fix would depend on a lot of things. And it likely would mean that you're going to want to change, you have 2,300 gallons per minute, so it's producing a lot of water. And yet you have water flowing out the bottom. That's an extreme hydraulic gradient. So you'd either want to abandon that lower part or else use you're in a screened interval, so I don't know if, that was Mills knife, if you recall. So it's probably got a void annulus from making sand, all that sand for all those years of use. So that might be a tough one to fix with an inflatable packer. I think you'd have to abandon the bottom in such a way that it got out to the annulus and sealed that off too. Fine sand, cement, something like that would get rid of that bottom. I just think that would be a tough one to fix out in any other manner. But it's a good question, and it varies from site to site. The more you think about these, the more there's what ifs and uncertainties. And again, this much you know, and all this mountain that you don't know. So you have to guess at things. Yes, sir.
Yeah, Marvin, I was just going to say that particular well, if you remember the numbers, at 2,300 gallons per minute, that lower zone was taking 102 gallons per minute under the Spinner survey.
That's right.
Yeah. So, and I think it's such a rare occurrence that I don't think we need to kind of it's somewhat rare for that type of occurrence.
It's rare, but I think it makes a good point, Neil. The point it makes is even if you aren't losing water out the bottom, you're losing production as your gradient reduces. Yeah. And we see that a lot. And in that case, it just exemplifies that extreme things can, I think it's more instructive than typical, I'll put it that way.
Yes.
Yeah. Any other questions? Oh yes, the code. I have the code for you. That was the best question so far. Thank you. All right, here's the code. MG, as in Marvin Glotfelty. 62, and EX, as in exit. So MG62EX. If anybody wants to touch base in the future, I do have some cards up there. Thank you very much.